So I'm going to present one set of results that I've done with collaborators at Stanford, in Europe, and here at the Earth Institute, in particular Radley Horton at the Center for Climate Systems Research that's housed at GISS, and Jason Smearden, who's based at Lamont Doherty Earth Observatory. But before I present those results, I kind of want to spend some time orienting everyone to the larger set of questions that my work engages and the logic that underpins it. And I think a great way to do that is with this quote from the Argentinian writer Borges, who said that the future is inevitable and precise, but it may not happen. And this actually makes a lot of sense to a climate scientist, and here's why. These are the possible evolutions that global mean temperature could take depending on our assumptions. And each line represents a climate model simulation. And in a nod to Borges, we can see that across the ensemble, warming is inevitable, and each one of those realizations is precise, but none of them may actually happen. And in part because of the large uncertainty that we see at mid-century in our prediction of temperature change, and in particular because different models give different answers to the same sets of assumptions, there's rightful concern that climate science may not be effectively positioned to inform the sets of adaptations that are going to become necessary as the world warms. Now, uncertainty in predictions of climate change from a multi-model ensemble, such as what generated that spaghetti plot, is typically viewed as having three distinct sources. Now, I tend to work on hydroclimate, so what we're looking at here is the percent of total uncertainty attributable to these three sources in a multi-model prediction in wintertime precipitation at the regional scale as a function of time. And scenario uncertainty, which is quite small, shown here in green, but looks kind of black on this screen, it arises from unknowable social, political, economic changes, and therefore what greenhouse gas concentrations in the atmosphere will be. Model uncertainty in blue arises from our knowledge of the climate system and lack thereof, and how that's actually reflected in our modeling choices of how best to simulate the Earth system processes that we care about. And because models choose to simulate things like cloud formation, turbulence, et cetera, differently, this actually becomes the most important source of uncertainty in this prediction of regional winter precipitation change after about 30 years. And finally, there's internal climate variability, and these are the random and natural fluctuations internal to the climate system that would happen in absence of people and their consumption of fossil fuels. And on short timescales, we can actually see that it's the dominant source of uncertainty in this prediction of winter precipitation. But unfortunately, this model uncertainty is actually likely overestimated, because in multi-model ensembles like the Coupled Model Intercomparison Project, or CMIP-5, which is the principal source of climate predictions used by the Intergovernmental Panel on Climate Change, or IPCC, to inform adaptations and mitigation policy, there aren't actually enough simulations with each individual model to effectively sample their representation of internal climate variability. And from a decision perspective, there are at least two problems with this. First, only internal variability and scenario uncertainty exist in the real world. And second, uncertainty from internal variability is irreducible in our predictions because it arises from randomness and the uncertainty associated with the butterfly effect. And it's actually really crucial to get the true size of this orange region correct, because it can confound decision making about climate change. And this shows why. Say we have a climate variable like, say, global mean temperature on the y-axis as a function of time on the x-axis. And we experience the green line, which is this internal variability, about a forced trend, which is the blue line. But the blue line only arises in hindsight, so we can remove it. And we can see that if we were to fit a 30-year trend to anywhere along this real-world green line, that we would get different but technically correct answers about the magnitude and sign of change in the climate. And so uncertainty really means that more than one outcome is consistent with expectations. And our expectations are shaped by what we know to be the full range of outcomes from internal climate variability. And at the same time, decision makers want to implement what are called robust adaptations. And these are decisions that are beneficial across the broadest range of potential outcomes, such as those induced by internal variability. as shown in the ranges in this cartoon, which shows a distribution of snow from more snow to less snow in the present climate, and then in 2 estimates of future climate under red and blue. And the red one has a partial estimate of this internal variability, while the blue one has a fuller one. And across the bottom, we see different possible adaptations to the magnitude change of snow response that corresponds above. And from a decision standpoint, the potential that internal variability's full extent is not being quantified in our multi-model projections of climate change is actually really critical, as under the red distribution, because the policy a decision maker adopts would be different if it's based on the ensemble mean or a partial estimate of internal variability than if it's based on the full range of potential outcomes, as we see in blue, and the highlighted management choices that would not be considered under the red distribution. So over the near-term decades, when proactive adaptations to climate change, like the building of new infrastructure, are actually most necessary to offset climate damages, internal variability has the potential to reverse the direction of anticipated trends in climate quantities on multi-decadal timescales and at near-continental spatial scales. And further, we want to know if things like the California drought, depicted by this set of images from Lake Oroville in California, we want to know whether or not they're a response to climate change, or whether or not they're just an anomaly in a complex Earth system that would have happened in absence of people and their greenhouse gas emissions. And we also want to know their likelihood in the future. And the answer really depends on our greenhouse gas emissions and randomness in weather, not how we choose to parameterize things like rainfall in our models. So getting robust and attributable estimates of uncertainty from their sources correct really matters if we're interested in informing necessary climate adaptations. In my research here at the Earth Institute, I engage in all of those sources of uncertainty. But today I want to focus on the scope of internal variability. And I want to talk to you very briefly about some research that tries to propagate an estimate of this internal variability into human impacts of climate change, such as what is the irreducible uncertainty in future population exposure to water stress. And so before I present the results, I just want to take you through how we get an estimate of the range of internal variability from a model, and not a truncated one like under the CMIP5. So one way to do this is with a climate model is to treat it the way we do with weather forecasting, which is to run a model many, many times, sampling the initial condition space to, say, come up with a probability of rain tomorrow. And this actually hasn't been computationally feasible with climate models until quite recently because of the decadal scale they represent. So what I'm showing here is an experiment that actually does this from the National Center for Atmospheric Research, and it's their Community Earth System Model, or CSM, Large Ensemble Lens, which is a rare set of 30 simulations of the same model with the same greenhouse gas emissions assumptions. Therefore, model uncertainty and scenario uncertainty are 0, and so we're getting a conditional estimate of the model's range of answers at 2080. So initialized from some point in 1920, our 30 new runs, the only difference among them is the weather at initialization. So the ensemble spread is really this irreducible uncertainty. So let's quickly shift gears and create a measure of water availability. And because it's meaningful from both a management and physical perspective, our unit of analysis is the basin scale, such as illustrated by the San Joaquin Basin there on your left. And we create a measure of the subannual magnitude and duration of basin scale water stress, as shown on the right, when basin scale water demand exceeds its supply. So what we're looking at here is from January to December, San Joaquin Basin's cumulative precipitation in P and cumulative evapotranspiration, ET, in green. And if ET were to exceed P, the San Joaquin would be drawing on its water stores in the form of soil moisture. And we call this a natural deficit. But there are also people in the San Joaquin, and they are demanding water, and in doing so, they are inducing their own evapotranspiration. And that's shown in H in the black line. And if we, and we can see that if we add the amount of ET induced by people and their consumption to naturally occurring ET, the San Joaquin enters a deficit denoted by this pink region and this P minus E T minus H. And this is something whose magnitude and duration we can calculate for all basins globally. And that's what I'm showing in these two sets of map. So the top is, I keep losing where the pointer is. The top is the global observed average magnitude as a % of annual basin scale precipitation, and the duration in the number of months per any 12-month period in the present climate. And I'm not going to go into the details of these maps, but implicit in this are all these managed and unmanaged systems that people have in place to ensure water supply during times of atmospheric shortfall. And because this... White is less than a month of deficit, or which would include potentially 0. So because this is a climatology, it implies that any small change to this measure would include potentially a host of management responses from a basin that would be institutional, legal, economic, infrastructural. So we can ask the question, given potential future population trajectories and future climate trajectories, what is the irreducible risk of increased deficits in their magnitude? So I'm just going to show some of the results, but here's for the magnitude. So this map is the 30-member ensemble of future risk, estimate of future risk in increased subannual water stress just past mid-century. And depending on population growth, we estimate about 2.8 to nearly 4 billion people that are exposed to a greater than 50% risk in the increased magnitude of these deficits. But you'll notice that there are quite a number of places with cooler colors, the yellows and the whites, like Southeast Asia and the Congo. You'll also notice that it's not within a basin either 100% or 0% corner solutions, suggesting that internal variability has quite a large role to play in this estimate, because this is just a 30-member ensemble, and risk is defined here as the number of ensemble members that agree on a direction and threshold magnitude of change. And if we look across the 30-member ensemble and exclude people's water consumption, we can ask what the full irreducible range in the magnitude of change in climate-driven deficits actually is. And we can see something really critical, that the majority of the basins, basin maximum, the basin average, the basin minimum, and then the basin maximum minus the basin minimum, we can see that basins have the potential for both increased and decreased water availability solely from climate noise. All this from just this uncertainty. But given this noise and some scenarios of population growth, what's the irreducible uncertainty in population exposure to future water stress? So what I'm showing in this box plot is the ensemble range in answers of the change in the number of people exposed to differing magnitudes of water stress, denoted across the bottom. Now, each box color represents a different population scenario associated with what are called shared socioeconomic pathways, or SSPs, that map onto the greenhouse gas emission scenario used to force this model ensemble. And we can see that if we just look at this first bin here, which is the change in the number of people exposed to net deficits of greater than 50% in magnitude, there's a range of nearly 1 billion people in some of these population scenarios. And I just want to remind you that this range is induced entirely by climate noise. The differences across the scenarios are induced by population trajectories and uncertainty in those scenarios. So despite this range, we can see that as we increase in the severity of the deficits, that there's kind of an ensemble convergence of additional people being exposed, which is largely driven by population increases. So just to quickly summarize, we can see that irreducible uncertainty means that there is the potential for basins to have both more or less water on multi-decadal timescales, and that this does not arise from differences in how the models choose to simulate things like rainfall. It simply arises from irreducible uncertainty in this model's predictions of climate change. And we really want to understand this range of outcomes better because it's the range of outcomes we live, not some undetermined mix of climate model uncertainty and real world uncertainty. And getting this range correct is really critical to position water managers to robustly adapt to things like the California drought. More widely, I think there's an opportunity to better integrate the requirements and insights from risk and decision science into climate impacts assessments to really manage this uncertainty, something that I'm trying to work on here while I'm at the Earth Institute. We optimize under uncertainty all the time, and I think that this is no different. It just requires rigorous estimates of the distribution of potential outcomes, which I've shown is possible to start doing. So I hope that I've updated your expectations of the varied forms that climate impacts can take with the same magnitude global warming. Thanks.
So this must be embedded in that somewhere. What is your population projection you use?
I can show you, actually. There they are across the bottom there. So these come from Brian Jones, who's now at CUNY, who did this work while he was at NCAR, working with Brian O'Neill. And these are 3 scenarios of population change expressed as a change in log people from the present day. And the point here is that what's really driving this range is kind of where circulation anomalies establish themselves within the model. And basins, you can see, are not uniformly increasing in population denoted by the red colors, or uniformly decreasing in population denoted by the blue colors. You can see that places are gaining and losing population based on this set of population projections. Now there are 5 SSPs, or shared socioeconomic pathways, and the different SSPs have embedded assumptions that are kind of narrative focused about how things will evolve in the future, and these are the 3 that actually map on to RCP 8.5, which is the representative concentration pathway 8.5 that's used for this set of model simulations.
But 8.5 is held.
8.5 is business as usual, and you know, I can show you that we're actually tracking at the 8.5 business as usual, at or above it, and so it's not a totally unrealistic scenario right now. I mean, the political intent versus actual implementation. I mean, that's the stuff of the Earth Institute, right?
I just want to make sure I understand. The irreducible uncertainty is natural variation, and you're estimating that by looking at within model runs based on different initial parameterizations.
So the irreducible uncertainty is the closest proxy we have within the model uncertainty of what internal variability is. Their internal variability is not necessarily irreducible to the extent that
I don't mean that. I meant internal variability is natural variability, which you're trying to proxy by multiple runs of the same model.
With just different atmospheric wind fields at initialization.
Right.
So the same sets of boundary conditions.
If you do that across the group of models, do you get the same amount of internal variability?
They would be different for each model.
Sure.
Yeah, so the range of irreducible uncertainty, if we were to, say, run this 30-member ensemble experiment with every general circulation model that's used in the IPCC,
right,
you would get different ranges of how big internal variability as represented by these models happens to be.
And would you get such big differences that you would say, these are not very good estimates, or would you take the average of those, or how do you actually handle that?
Well, I think, you know, like with anything that's kind of model focused, it should be model for purpose, and I think that should be governed by the question that you're asking of the models. And I think, you know, there are a number of different philosophies about what it is that we can and should claim with responsibly with these climate models, and whether or not frequentist statistical assumptions map on to the CMIP-5, right? Whether, you know, that we know from a genealogical perspective that these models are not statistically independent, they share code,
right.
Which kind of undermines that assumption.
They share code and they share basic physical logic.
Absolutely, yeah.
I hope.
Yeah, so you'd expect some correlation, but the extent to which the irreducible span that we see in the CESM, which is a set of results that I presented today, is a function of the model choices themselves. That could be different. I think from a decision perspective.
What I'm wondering about, you said at some moment, and I may have misunderstood, that you thought the estimate of the model uncertainty was an overestimate.
Yes. And the reason,
and that surprised me intuitively.
The reason that is because of the way that quantification is constructed, right? These curves are defined relative to one another. And so if you're changing the area, the fractional uncertainty associated with internal variability, you are necessarily changing the fraction that we attribute to climate model uncertainty. And in particular because, you know, the CMIP-5 give widely different results on things like hydroclimatic change, whether or not wet places are going to get wetter or dry places are going to get drier. People kind of chalk that up to models need to improve. And the nuance here is that I'm saying if you run the same model many, many times, you get the potential for increases and decreases from a hydroclimatic perspective, which says that it's not as simple a story as we need to wait for models to improve. So really, I think the point here is that this is used from a political standpoint as a justification for hand-wringing. We need to have science kind of improve to a point where we know with certainty what the change is going to be. And the chaos of the climate system, insofar as we understand it, says that there is, even with hitting a hammer in the RCP 8.5 scenario, that there is the potential for increases and decreases in precipitation and evapotranspiration.
So one thing you could do, or presumably have done, is that certain outcomes of the model have very low internal variability, like mean temperatures over certain periods, but precipitation much higher variability.
Absolutely, yeah. You'd see a starkly different partitioning of the sources of uncertainty as a function of time if we were, say, looking at regional winter temperature. Right. You would see the scenario uncertainty balloon out, particularly around 2050, and it would become kind of one of the dominant, if not the dominant, source of uncertainty on that longer time scale. There's much greater convergence in the models on what temperature change is going to be, and other kind of quantities that are mediated by temperature.
I haven't seen that point. I mean, the point you're making, I haven't seen that clearly articulated, that the within model variability based on initial conditions is very high for the following kinds of outputs and quite low for others. The temperature, model by model, is not highly variable from an internal variability point of view. Initial conditions don't matter very much, but precipitation could matter a lot, for example.
Yeah, I mean, the point of an initial condition ensemble like this is that we don't have perfect atmospheres of the atmosphere and the ocean state and the land surface everywhere. Sure. And so, just given observational error, there is the potential that we wouldn't get the true pathway of precipitation change. And I think what this tells me, and I think is kind of an increasingly popular philosophy of how to interpret model results, is that the model mean should not converge on future truth. It's that the model ensemble should bound truth, right? That it should fall within its range. And I think this kind of advocates for that paradigm of interpretation.
But is there a way you could nicely summarize temperature? We've got down, or the model has down in some sense, but precipitation, it's intrinsically highly unstable?
I mean, I would be uncomfortable with that first statement because I
But you
think
could find that out. I mean, that's an
yeah,
empirical
no,
point for
I
me.
mean, I think, and that's what we're trying to do. I think one of the key questions there, and is that's implicit in this, is whether or not variability in the future climate is the same as in the present day climate or in the historical climate. And there are a lot of people doing really good work trying to disentangle that. And
Right.
so it's unclear whether or not that first statement that we have, I mean, we have pretty good thermodynamic constraints on temperature change, but at higher spatial scales, at finer temporal resolutions where people are and decisions are made, yeah, there's this chaos could be pretty big.
Yeah, okay.